doing two variable statistics, right? Scatter plots. So we've been talking about there being associations or correlations between the two variables. And then this one is about nature versus nurture with twins. So if twins don't grow up together, right? Is there a difference, or identical twins, is there the similarities? Okay, so let's look at that real quick. It's a short video. Then we're going to do lesson 3. And then there's a short exit ticket for like a homework grade kind of a thing. Okay, it's that difficult. So let me go back into find our video. There it is. All right, Party Sabetti, give it to us. We love this lady. There, oh, there she is.
Hi, I'm Party Sabetti, and this is Against All Odds, where we make statistics count. 3-year-old Kevin and Alan are twins. They're being fitted out with motion detectors for a study of one of the oldest and most controversial questions about what makes us who we are: the genes we are born with, or the environment we grew up in. It's a question Kim Sedino is often asked once people know what she does.
They're usually disappointed because they don't usually say, how much is it? They say, is it genes or environment? And I say it's both, and that's not the answer they want. They always want to pit one against the other.
The classic correlation study of genes versus environment was done in the 1980s with subjects like Jerry Levy and Mark Newman, identical twins separated at birth and raised in different families. They didn't meet until they were in their 30s. Mark recalled his first impression of his twin brother.
He's big like me. He's got a big nose like me and glasses like me. And he was wearing a baseball cap, and when he pulled the baseball cap off, I'm like, oh, hell, he's bald like me.
As well as looking alike, the two had a lot of other things in common. Mark installed burglar alarms, Jerry fire alarms. Both held their beer cans with a pinky at the bottom. And both were captains in volunteer fire departments, a remarkable coincidence to all but the twins themselves.
Well, I guess I always wanted to be a fireman. And then I find out that my brother's a fireman. It's not strange, but he's got to be a fireman. Only because firemen aren't made. Firemen are born.
Does that mean being a fireman is genetic? Stories like Jerry and Mark's might make you think so. Since they were raised in different families, the most likely explanation for their similarity lies in their genes. Seeing an opportunity to assess the relative roles of environment and heredity, during the 1980s, University of Minnesota psychologists studied dozens of identical twins raised apart.
Who's gonna go first?
You.
Like the other twin pairs, these recently reunited sisters underwent a week of intensive testing. The question was how similar they were. In other words, how closely correlated were they for certain traits? These included not only physical traits, but also psychological traits, such as how they react to the imminent popping of a balloon. The twins were also given personality and intelligence tests. The same battery of tests was also given to twins raised together.
In the case of identical twins reared apart, the only reason they ought to be alike is that they share genes in common. So the measure of correlation or similarity between them reflects the effects of genes. The contrast is identical twins who are reared in their own family. There are two major reasons why they should be alike. One of the reasons is common genes or heredity. The other is common family environment. Consequently, you can compare identical twins reared together and identical twins reared apart, and the difference in the size of the correlation tells you the influence of the common family environment.
So how do you assess the size of the correlation? Well, as we've seen many times already, you can get a pretty good idea simply by looking at a picture of the data. Here we've plotted the heights of pairs of twins raised apart, with the height of one twin, say twin A, on the x-axis, and the height of twin B on the y-axis. We can quickly see that the taller one twin of a pair is, the taller the other. There's a positive correlation between the two. Now, this isn't too surprising for a physical trait like height, but what about those personality traits the Minnesota Twin Study also measured? This is a scatter plot of a personality inventory study given to pairs of identical twins reared apart. And while the relationship isn't as clear as it was for height, the points do tend to increase together. Remember, the twins were raised in different families, so the fact that a correlation exists at all can only be attributed to their common genes. We can compare these two scatter plots more objectively with a direct measure of correlation denoted by the letter R. Here's the formula for calculating R. It's actually not as complicated as it looks, but in practice, most people use software or a calculator that finds R from keyed-in variables of x and y. The value of R is always a number between -1 and 1, with -1 being a perfect negative correlation, and 1 a perfect positive correlation. So let's see what the R is for those two scatter plots of twins raised apart. For height, R is 0.92, very close to the perfect correlation of 1, which is what it would be if the heights of the twin pairs were determined solely by their genes. For the personality study, the correlation is 0.49, not as strong as for height, but still suggestive of a strong genetic influence. Studies like that with Mark and Jerry were only possible back when it was common for identical twins to be separated when placed for adoption.
Nowadays, we don't like to separate twins. And so even if they are reared apart, we try to have some contact between them. So they're not truly reared apart in the way that they would have been in the Bouchard study.
So in her study of the role of genes and environment on an important personality trait, Kim Sedino is taking a different tack, comparing fraternal twins, like Kevin and Alan, who share approximately half their genes, and identical twins, like Sam and Ethan, who share all their genes. The motion sensors on the twins record their level of activity in a variety of play situations. Previous studies have shown that how active a toddler is at the age of 2 or 3 is a strong predictor of difficulties later in life.
It's related to behavior problems, aggression, externalizing problems. It's been shown in some studies to be related to academic outcome. It's also correlated with extroversion, so how outgoing they are.
Here's the scatter plot of the activity level of identical twins as observed in the lab setting from an earlier, similar study. And you can see at a glance that the correlation is pretty good. In fact, when Kim Sedino computed R, it turned out to be 0.48. Now here's the data from fraternal twins. The picture alone suggests that the correlation between the twin pairs was lower, and the computed value, 0.26, confirmed that the correlation between the activity levels of fraternal twins is much less than that between identical twins. Since the environments the toddlers were raised in and studied were the same, the difference in correlation can only be accounted for by the genes they inherited. Case closed, right? The genes you're born with, much more than the way you're raised, determine how active you'll be as a toddler, and in turn, how well you do on important social measures as you grow up. But wait, there's a wrinkle in the story. In that previous study, the twin pairs also wore the motion sensors for a few hours at home, and the scatter plots from those data looked very different from those obtained in the lab setting. The difference between identical and fraternal twins has largely disappeared, with the R value for identical twins now at 0.87 and for fraternal twins, 0.70.
The fact that we're finding the correlation for fraternal twins in the home that's much higher than 1/2 the identical twin correlation tells us that in addition to genetics contributing to familial resemblance, it tells us that the shared or common environment is also contributing to familial resemblance. So things that are common amongst the twins, environments that are common amongst the twins are making them similar as well as genes.
So, for all you still wondering if you were shaped more by your genes than by your environment, remember how Kim Sedino always answers that question. It's both. And it's through correlation studies that she is able to tease apart the contributions of each in different circumstances.
We do now very fancy models. We don't usually compare one correlation with the other. But at the root of these very fancy models are the correlations. They're the basis of it. So although we do these very fancy statistical analyses, at their very core, it all depends on the correlation.
I found Kim Sedino's use of statistics to gain insight into the effects of genes on the human condition especially fascinating, because that's something I do in my own research, where I look at how genes can confer resistance to deadly diseases like malaria or Lassa fever. But that's a topic for another time. Until then, I'm Pardeep Sabeti for Against All Odds. We can compare these two scatter plots more objectively with a direct measure of correlation denoted by the letter
I
R.
wanted to find.
Here's the formula for calculating R. It's
a
actually
specific
not
picture.
Mark and Jerry's influence.
So there it was.
The twin pairs were determined solely by their genes.
Come on.
For the personality study, the correlation is
So even though that correlation feels so very weak, right, to us as a number, its value is still important. There was ones that were really, like, it felt like there was the 0.4 versus the 0.2, and 0.2 were like, that's no correlation at all. But when you're comparing correlations, that does still provide some aha moments or some information about what to study further. So it's not just the correlations that are close to 0.9 or negative 0.9 that we care about. Does that make sense to everyone? Okay, I just wanted to make that point before we go on. All right, so that was our twin study. And what's interesting about twins and all of that, they said that, they don't separate twins like that. And in fact, like the idea of open adoption is something that's much more out there. Now, something that's very interesting is my son is the result of a donor, right? So my son has half siblings like all around the United States. He's got like 6 of them. He doesn't know anything about that yet. But eventually he has the right to meet his sperm donor father, his biological father, to see that relationship. And then also through bank, different ways you can meet your half siblings. So it will be fascinating for him if he wants to pursue that information to do so, right? So this whole genetic piece versus nurture versus nature is fascinating, and has been. So when we go to our next thing, we're going back to, once again, a very simple situation to talk about that correlation coefficient calculation. And the story that we're going to go back to is the one with the donations to the small college. But there's some interesting things about this that we want to make sure we still understand. The correlation coefficient is a lowercase r. This is its formula, and it has no units. So it's that idea of it's a measurement, kind of like how pH is a measurement, how like 5 stars, 1 star, right, is a measurement to give something a grade. Now, performing this calculation by hand is tedious, but it's not terrible. And we're not going to calculate it by hand, but I'm going to kind of show you how your calculator can adapt to that. I'm not going to force you to do the whole thing, but I want to make sure you understand the parts of the formula. And so did everybody have a chance to put this in their calculator? Okay, so if you haven't, maybe you could do it while I do some chatting as well. You want to put in 2 columns in a table. I called this one years, I think, and I called this one money, just so you can follow along on my calculator. You can always put X and Y, no big deal, right? Things like that. All right, so I'm going to go back up to this formula just to make sure we understand the variables. N is the size of our sample, right? And so in our situation down here, our sample size is 7, right? We have 7 different pieces of data, pairs of data. Now up here, we have X, which is one of those X values, like 1, 10. And then we have subtract X bar, and we know what X bar is. It is the mean, it's the sample mean of the X's. Well, guess what? That means we're looking at the difference between those 2 values. Is it a positive difference? Is it a negative difference? What's happening there? They're doing the same thing for the Y values. Once again, a sample mean. And then that difference is divided by these S values are the sample standard deviation. Okay, so not only are we taking the difference, then we're dividing it by the spread number, right? Which, if you think about that, like say, and we're going to go through it, but like say the average is 15. Well, that means 5 is 10 away, right? And then maybe the standard deviation is 9. So then it's almost like making a percentage Like what percent of the standard deviation are you away? Does that kind of make sense to everybody? Part divided by whole. And then the formula starts to get a little crazy because then we multiply those things together, add them up. That's what your summation is, right? And then have this fractional thing. Okay. So I am not saying that this calculation is easy, but the parts of it should make sense. If I want to understand correlation, I want to know how far away these points are from the averages. All right, so if your data's in your calculator, you should have something that looks kind of like this. And I'm only going to force you to go through the first part, okay? The thing that I want to show you, and I'm going to put my cursor back in this column. Whoa, slow down there, cowboy. Is that under menu, and so do this part with me if you don't mind. In stat calculations, where we do number 4, right? And under 1, do you guys see how it says 1 variable statistics and then 2 variable statistics? We're going to look at that right now. And this is the only time we will probably ever look at that. Does that make sense? Because we're just going to try to understand this formula. So you want to go to 2 variable statistics, and then you need to tell it the names of your columns. So your X column is years. Don't mind all the junk that I have in mine. You should only have 2 things there, right? Year. And then the Y list is money, right? And if you have your cursor in B, it'll say put my results in C. Okay, so press enter when you're ready. And if at any point during this whole experience, your calculator goes, just watch, please. Does that make sense? Be polite and watch the process. Okay, so we do that. So now I want you to look at what's happening here. So the average number of years out of college, 12.5. Does that make sense? We had values from 1 to 30. The standard deviation or the spread is 11 years in either side of that. Okay, we go farther down into this list, and do you see how now it moves into Y bar and Y, standard deviation. Okay, so those 4 values we would pull and start to use in our calculator. So I'm going to show you one more thing. You do not have to do this with me, and then I'm going to show you a mess because I did the whole thing earlier today. And then we're going to do the fast way to do it, which of course your calculator can do it like this. Okay, so I'm going to go to a blank spreadsheet, and the reason why this is kind of cool is because I have named lists already. So the minute I go up here and type the word year, year. Do you see how it turned like mine is year? So do you see how it goes from italics to bold upright? If I hit enter, look what happens. It just pulls the data into a new spreadsheet. Okay, and I could do the same thing up here for money. And the reason why I definitely want you to, or I want you to do this is so you guys can see what's happening. Okay, so now this is what I want to show you. Remember how I said this equal sign is super dangerous? It's because that's where you put formulas, just like you do in Google Sheets, and we're going to end up doing this all in Google Sheets, working with bivariate data, not this particular calculation. But going back to what it said in the notes, do you see how it says X minus X bar? All right, so on your note page, I do want you to write down that information. So we have X bar, and I have this written down, so if you don't want to flip back and forth. X bar was 12.6. So the average of the years was 12.6, and the average of the money donations was 8.1. Okay. All right. So if I go back up to this formula, I want to take each individual one and subtract 12.6. And so this is why, once again, I think spreadsheets are cool. In my equal, all I'm going to do is put year. Where is it? Y-E-A-R. And it became bold. Subtract. What was my average? It was 12.6. And then watch what happens. Boink. So do you see how it's finding the difference automatically for me? And so the deal is this. We would then do the difference for the money, right? And then we'd have to divide those by standard deviation and multiply them together and then add them all up, right? Well, just stay with me. Let me see if I can get over to the beginning. So here we go. So I did money, year and money. Then I did year minus 12.6. And then I did that divided by 11 because that was the standard deviation, right? Okay, so now I'm going to do all this stuff with y's. I'm going to do money minus the 8.1, and I'm going to divide it by that standard deviation. Then I did notice how I call them chunk. I didn't know what to call them. And then I did the product. I multiplied them together. And then the very last thing I had to do is I ran one variable statistics to get my sum. Okay? So, when I did all that, does that make sense, everybody? I got negative 5.47, we'll just say 8. We'll leave it at that. And then the formula above says do 1 divided by 7 minus 1, which is 6, right? So 1/6 times this thing. All right. So when I did that on my calculator, I've got an R value of negative 0.913. So this was my kind of by hand version. Okay. You're never going to have to do that. But I want you to understand where the formula comes from and how it works. Are we ready to do it the fast way? Okay, cool. So let me go back in and just sit down for a second. And this is on your reference sheet. And here we go. So if you need another page because you have messy stuff, just add another page. Doesn't matter. Or you can just watch me and you'll be doing it because, oh, not that. Doing. I need a table 4. Okay, so I'm going to go back up and say that this is year, just so you guys can see what I'm doing. You actually don't, it would talk to itself no matter what. Like, I don't have to redo this to be able to do the calculation on this page. Okay, but now I'm ready to go do a linear regression equation. So I go menu, and I go to statistics, and I go to stat calculation. So that's still the same. And down here, there's 2 different versions for linear regression. Do you guys see that? You guys know MX plus B. Statisticians use A plus BX. Okay? So so it's basically 414. Does that make sense? I hit that. What's my X list? Year. What's my Y list? Money. Am I okay with putting it in column C? Yes. And this is what you're used to kind of seeing back when you did this in Algebra 1. You get an A value, which is your y-intercept. You get a B value, which is your slope. Notice that the slope is negative. Do you guys see that? Okay. So now I get R squared, which is always positive. Right? We want something that can be positive and negative. And the R value calculated for reals is negative 9.9077. So not too bad. I was pretty close with my crazy calculation. Negative, so we go back in here, negative 0.90, I'm just going to put 8. Usually we do correlation coefficient to 3 decimal places because it is like that sign of strength and weakness. Okay? 2 or 3. 1 is never enough. Sound good? Okay. So if you turn the page, beep, this was the graph we did previously. I just copied and pasted it into here from a previous year. Basically, we knew that it was a negative correlation, right? It was going downhill. We knew it was fairly strong. So once again, on that previous page, we had R equals negative 0.908. That's what we got from our calculator. Do you guys agree that that is strong, negative? And because it's an R value, it is also linear, right? Strong, negative, linear correlation, association between the two variables. Okay. Now this is what's kind of cool, right? We know that this is, so first of all, on our number line, -1 is here. Our correlation coefficient is right there, right? That's our R value. The other thing that's really important is everything actually does reconnect to that X bar, Y bar kind of guy. So we go back to the X bar, Y bar, X bar, Y bar. That's a coordinate pair. X bar, Y bar. And when we calculated it, we got 12.6 and 8.1. I want you to plot that point on your graph, the X bar, Y bar number. So if we go over 12.6, so remember 12 was the second line, so 12.6 and up 8.1. So we're going up here, there's 8, 12.6. So it's going to be right about there, I think. This is X bar, Y bar. That point is guaranteed to be in the line. So if we were to then take your straight edge, if you picked one up, and you would try to make a line, like your line has to go through that point. So I'm just going to kind of play around here, and I might not be able to hit it perfectly. I think I have that part too high. So I'm going to do this for a second. Select, see if I can get this point and bring it down. So maybe my line is something like that. Does that kind of make sense to everybody? It's doing this crazy calculation of with the X bar, Y bar, which is the average of the two things, and it's looking at the distances between all the other points. And we're going to see how that equation is made in a different lesson. All right, so did the R value support our original interpretation? Of course it did. We thought it was a fairly strong linear negative association. As the number of years out of school increases, the amount of the annual contributions decreases. I think we've already beaten this part, but let me just make sure. R is close to +1, -1. It's easy to understand why it's strong. As it approaches 0, yes, we do start to use those other words, such as moderate or weak. You're definitely looking to see if it forms any other pattern, like we saw one that was quadratic. If we have a quadratic regression, we don't have an R value at all. R is strictly for linear. And then once again, if you're comparing correlation coefficients, it might be okay that you're in this weak zone because you're making a comparison to something else. All right, so if we turn the page and we have 9 o'clock in the morning, it's great. All right, here we go. So we are going to play with another set of data, but we're going to break the work down. Okay, are we ready for that? I would recommend that you just empty your calculator, right, and get a brand new document at this point. I think it's going to be easiest. All right. And then let's do this. Everyone is going to do height. Okay. You guys do arm span, okay? All right, you two. Actually, you two do shoe size, okay? So that B and A, and then we have 2 or 3 of you doing this last one, okay? So Justin and Will and there, okay? So everyone has to have height, and then you're going to have one more column. So you're going to have 2 columns of data in your calculator. Cool? All right. If you're confused, let me know. Cool. Just Control Doc. Okay. You have your data in? You have your data in? Data's in? Bella? Okay. Billy and Raphael, are you guys data ready? Okay, cool. So you guys are over, you can have your cell maybe in column B, right? And you're going to go menu 4, 1, that's the easy part. And you're going to choose number 4, okay? 414. And then everybody is going to have height, right, for their X list. And then whatever you have for your Y list, you're going to put there. And then you can hit OK. I'm just going to escape out. And go back to this. Okay, so let's just check here. All right, so Bailey and Raphael, did you guys have R equals 0.9528? Yes. Okay, 0.9528. So everybody go ahead and fill that in. Okay. Okay, now we have height and shoe size. Okay. Okay, Bella, did you guys have 0.9323? Okay, 0.9323. And then, let's see, so you guys had something a little bit smaller, right? Did you guys have 0.6762? Good. So these were all positives, okay? So if we're going to go ahead and do interpretations, we need 3 words, right? You need a word about strength. You need a word about direction. And then the last word is just repetitive. I don't know why my board slowed down. There it goes, direction. And then the last word is just saying that it's linear, right? So here we go. What do you guys think about the first two? Same thing? Strong, positive, linear? Yeah. So strong, positive, linear correlations or associations. Same thing here. Strong, positive, linear. Okay. And then our last one, we'd probably throw it down into moderate. Do you guys agree with that? Okay. So it's moderate, positive, and linear. So quickly, just to kind of make sure we understand where this data came from, 2 years ago, I had people tell me their shoe size. And for women's shoes, we added 2 to have it all be in the same system. Okay. And then we did hand span, which is the measurement from the end of your thumb to the end of your pinky. Okay. So those were the different measurements we compared. Then I did have a freaking massive list. So what I did do is I sorted it by height, and then I took a sample out of it. So it wasn't random. It was kind of stratified. I took, I took people in each height, and then I took a variation of what I found within each height, kind of representation. So I took every third piece of data. Does that make sense? So that way it would make sure that I was getting something that would represent the true population of that sample. The sample that represents the sample. Something like that. Okay. So before we clear this out of our calculator, I just want to show you how you can make the picture, and then I want you guys to show each other's pictures. Does that make sense? Okay. So when you're in your calculator, to see any sort of picture, don't we go Control, add a page, and do a 5? Okay. 5.